So we looked at this section, which included the Antarctic bottom water, North Atlantic deep water, Antarctic intermediate water, and something called oceanic common water, which is the mixed up stuff. So the three main things you remember, maybe you want to remember four things, are the Antarctic bottom water, AABW, North Atlantic deep water, Antarctic intermediate water, and the Mediterranean intermediate water. These are kind of the dominant water masses that are filling up the ocean. And as I had mentioned before, there is this vast world ocean, several kilometers deep, with 90% of the water sitting below the picnic line. And that entire water mass is coming from these few sites in the Labrador Sea, in the so-called Jin Sea or the Greenland, Iceland, Norwegian Sea, where evaporation is high enough, temperatures are cold enough that you're forming North Atlantic deep water, which is sinking. And you can see this cold branch going south in the western boundary, coming into the Southern Ocean, mixing with these Antarctic bottom water and Antarctic intermediate water forming in the Ross Sea, Weddell Sea regions. The Mediterranean intermediate water is not shown, but that also becomes part of the thermohaline circulation by mixing up here and joining the thermohaline circulation. All these waters circulate several times in the Southern Ocean, get mixed up, and then inundate the deeper parts of the Indian Ocean, as you can see the cold waters coming in, and the Pacific Ocean, as you can see the cold waters coming in. The North Pacific, as we said, is very big. It's cold, but it's too fresh. A lot of fresh water coming in from the Arctic through the Bering Strait in the northern tip and making for a very fresh water. So unlike this North Atlantic region, which is so close to land and has the Gulf Stream coming in and bringing warm waters and evaporating, and the very, very cold Labrador current coming in and creating North Atlantic deep water. Okay, so the time scales of how quickly the waters go through the Indian and Pacific Oceans are very different, because the Pacific Ocean is a very vast, deep ocean. Indian Ocean is relatively shallower, as well as it's closed off to the north. Okay, these things matter because the Indian Ocean is warming very fast under global warming. So the cold waters coming in and becoming surface waters and going out is very important in terms of how fast that can happen. And you will see that the warm return branch is kind of complicated. So the return is happening as warm shallow currents from the North Pacific through the Indonesian through flow that I mentioned, which creates a Lewin current that is going opposite to the wind directions as opposed to the eastern boundary currents here and here. And that is going to come in here, turn around the corner south of Africa, and go north, cross the equator, cross equatorial circulation happening at the boundaries, because we need to change the sign of the vorticity because of the dynamic boundary of the equator, and back to the regions where North Atlantic deep waters from. So it becomes part of the Gulf Stream, North Atlantic drift, North Atlantic current, and so on back into the Jin Sea and sink again, right? This is the so-called global conveyor belt, a terminology that was coined by Wally Broecker, who was a giant in the field, did incredible amount of work, died very recently, worked all his life at Columbia University, Lamont Doherty Earth Observatory. He has written many good books you can read. So enormous presence in the ocean field, the climate field, was the first guy also to warn us about global warming, looking at the carbon dioxide data collected by Charles David Keeling in Mauna Loa over Hawaii and so on. So sinking waters take heat and carbon dioxide with it, and they mix it up. The water that goes to the bottom of the water can circulate there for a long time, hundreds of years, more than 1,000 years before it comes back to the surface. How do we know the water is coming back to the surface? Basically, you can imagine a bathtub. If the water is sinking at one place, if the water gets stratified and becomes equal density, then the water stops sinking. So if you go here and see that water is sinking, that means it continues to remain heavier than the other water, which means the other water is getting lighter over time. So heavy water is sinking, slowly it's getting lighter. That's why the heavy water can continue to sink. That's how we know. It's a very simple explanation, but that's what happens. So let me stop this here and come to the last bit of the chapter on wave energy in the next slide. Thermohaline circulation, density-driven circulation, is very important, has lots of details. It affects the oxygen profile, the carbon dioxide profile, and so on that we looked at before. So make sure you understand the fact that deep water, intermediate water, and so on are forming in a very few places, but they are sinking so continuously, taking down so much water that they're able to inundate the rest of the world ocean, creating 90% of the deeper waters below the thermocline. Very important part of the climate modulation, because the heat that sinks can remain away from the atmosphere for a very long time. So if the ocean stops sinking or reduces the amount of heat and greenhouse gases it can take down, then you will begin to speed up the global warming rate, right? So the global warming is very heavily modulated by the thermohaline circulation, something you must remember.